Right. Good morning, everyone. Thank you very much for having me. So my name's James Dark. I am a PhD student at the CEA in France. My PhD is based on doing multiphysics modeling of different components for a tokamak fusion reactor called DEMO, which is the successor to ITER. And part of my PhD has been developing a hydrogen transport code called FESTIM. I'm going to talk to you a little bit about today about what it does, why we care, and how we're upgrading it to use the latest Dolphin-X engine. So this is a cross-section of ITER. It is a fusion reactor that's being built in the south of France. To give you a kind of sense of scale, that's me. So that's 1.9 meters there. So the whole reactor is about 30 by 30. It's a torus, it's a tokamak type reactor, which means we have a kind of torus-shaped vessel. So it's a bit like a donut. We have a series of magnets going in the poloidal direction and in the toroidal direction. And the idea is that we create a plasma and it's contained within the torus and it doesn't touch any of the walls. And we have a central solenoid in the center, which induces a current and kind of puts a little twist on the plasma. So it kind of turns in like a kind of helical direction. And yeah, so the idea with nuclear fusion, instead of taking something really heavy and unstable and splitting it to create more stable atoms, we take two very light atoms and fuse them together to create something more stable. And yeah, we can create energy this way. And obviously, the lighter the atom, the easier this is. So we want to use different types of hydrogen isotopes or hydrogen in general to do this. And the most optimal reaction we have so far is a combination of two different isotopes of hydrogen, deuterium and tritium. And these two fuse together to create a really high energetic neutron and a helium atom. And basically, once the plasma kind of flows around, it eventually interacts with a component that's called a diverter at the bottom. But we have a lot of issues and challenges with handling tritium. First and foremost, it's extremely radioactive. It has a really short half-life of about 12 and a half years, which means that it's very, very active and very, very dangerous for humans. Hydrogen in general can cause various different material embrittlement issues in metals. And as a result of its radioactive nature, it means that it just doesn't exist in nature and it's extremely expensive. I think it's like the third most expensive substance per gram behind antimatter and something else. So we need to generate tritium ourselves. And actually, the most effective way that we can generate tritium is by using the high energy neutrons that are born inside the plasma, because when neutrons react with lithium, it creates tritium. And so the idea is that we're going to fill components surrounding every part of the reactor, completely surrounding it with as much lithium as we can to generate tritium, which we can then take out and process to use as fuel, again, kind of creating this elegant, self-sustaining fuel cycle. And so we need really detailed hydrogen transport models of how hydrogen and tritium moves around in different components within the reactor itself, in the breeder blanket, and also all surrounding components. But the reactor itself is just one small part of a whole global fuel cycle. And actually, we're going to need hydrogen transport simulations in all these different components because tritium is very expensive, it's very precious, and we need to make sure we know exactly where it's going, both because, yeah, it's expensive, we want to get as much of it as we can, and for safety side of things as well. But there are various different phenomena that kind of considered in hydrogen transport. So first and foremost, hydrogen moves within a metal lattice in its monatomic form, and it diffuses around. And you can describe this with a Fickian diffusion or Poisson-type diffusion. But in reality, metal lattices don't look nice and ordered. They're full of different defects from different kind of vacancies or interstitials and impurities within the lattice. And these different defects act as trapping sites for hydrogen. And you can imagine these like energy potential wells, where basically as hydrogen is diffusing through, if it encounters a defect, it's more energetically favorable for it to stay in these defects. And the only way we can remove them is by giving them more energy, i.e. heating up the system and allowing the hydrogen to escape. But there's different kind of fancy surface reactions that we want to consider. And also, if hydrogen has enough energy as it's approaching a metal, it can implant deep into the plasma, cause it or into the metal structure, causing damage in the process, creating interstitial atoms and stuff. So these are all the different kind of phenomena that we want to consider in hydrogen transport modeling. But we also want to do it on really big, complex components like this. And this is where we can leverage numerical methods to be able to model more complex geometries such as this. And we do that with a neat little tool that we've created called FESTIM. So FESTIM stands for Finite Element Simulation of Tritium and Materials. It's based on legacy FEniCSx for the moment. It's capable of multi-material simulations. We first started development in 2019, but we became open source almost 2 years ago. And since then, we now have over 14 contributors, and we're used in more than 20 different institutions around the world. And we have a very scientific metric here of our popularity with the stars increasing by the day. And you can see where we've run different workshops and kind of forcing people just going on their laptop and pressing the star button themselves. So these are the macroscopic rate equations that we use to describe hydrogen transport. We basically separate out what the trapped population and the mobile population of hydrogen moving along. And we can describe our mobile population CM with a diffusion term, a source term, and a coupling term to our trapping. So for each trap we consider in each metal, we can describe it basically as the competition between trapping versus detrapping. And so yeah, nothing crazy complicated compared to what we've seen this week. Relatively simple equations, but the issue that we have is that we have a lot of Arrhenius laws within these equations, and so they're very, very sensitive to temperature. Thus, in FESTIM, we felt it was pertinent to also solve the heat transfer equation, and this can allow us to have much more complex temperature fields in our models, which we can then feed into a function to have feed into our hydrogen transport equations. In hydrogen transport, we also consider a kind of novel material interface condition. This is derived from having continuity of partial pressure going across a material interface boundary. And we can describe this by having the ratio of the mobile population over the solubility of hydrogen in that material being constant across an interface. So with two different materials, you're likely to have two different solubility values. And this results in strong discontinuities that we'll see at interfaces between materials. I'll go more into this later. FESTIM is completely verified and validated. We have a whole series of different like MMS tests within our CI, and these equations have been validated over and over with different kind of experiments that we can use. And we're also in the process of developing a new VMV Live Jupyter book. And the idea with this is that we can have all our VMV tests available, we can show the code, but it means that we can update it for every single new version of the code as well, rather than just having a static publication. And so this is the kind of things we can do with FESTIM. We have all sorts of different applications for all different areas all around the tokamak, from different components like the monoblock to a breeding blanket to various different experiments that we have, including a really cool one we have at MIT at the minute where we're irradiating some lithium inside a small cask and then generating some tritium that way and extracting it. It's really cool. And then some different types of extraction systems to look into the effects of instabilities in the plasma. So FESTIM is a really versatile tool, and we've really designed it to be as open as possible and with various different applications within fusion, but also outside in different areas of hydrogen research as well. But we have a series of different limitations and issues with FESTIM at the minute. First and foremost, we have some dire performance issues with scaling, and this is largely due to the methods that we use to enforce this interface condition. We'll go into it in the next slide. It's not great, but it works. We've also built up a whole bunch of technical debt as we've been developing, because in the very beginning, we had a lot of hard-coded physics in the very center, and this has really inhibited a lot of development of any cool new features. And also, legacy FEniCS has been deprecated, so obviously there's certain bugs or features that are never going to get fixed, and we can't take advantage of all the new cool features that are being implemented. So all roads lead to Rome, and but we're also taking this opportunity to kind of start from fresh and take everything that we've learned in the last 4 years and kind of start from the beginning and reimagine what the foundations of the code should look like to make it as parameterized as possible and kind of allow the code to grow. But I'm just going to talk about one bottleneck that we've had in our kind of conversion to Dolphin X, and that is how we handle the interface condition. So we don't use any kind of fancy DG methods. I'm not going to get you excited about that. We basically have a little hack where we just introduce a new variable that we call theta, which is equal to the mobile population divided by the solubility. We then replace this theta value into all our transport equations, so we get a nice kind of continuous solution going across our domain, where we just use very simple linear Lagrangian elements. And then in post-processing, we then go through each subdomain and multiply the mobile population by the solubility value. And we can project this into DG space, so we can get these nice kind of clear-cut concentrations, and we can get this jump. This method works. It does not scale well. It's awful. If we try and do anything in 3D in parallel, this little fix ends up taking about 80% of our runtime. It's awful. And so we want to do things differently in FESTIM 2.0. And after a lot of consultation with Dokken and with Joe, we've actually been shown that what we should actually do instead is use a more novel method in which we still have our continuous Galerkin elements in the materials, but we have DG elements on the interface instead, where we can define our jump and hopefully kind of solve for the mobile population directly. But to do this, oh yeah, but there's also like other interface conditions we want to consider as well. So we want to keep it general and parameterizable. But to do this, we need you. We need some FEniCS experts. So we have a minimal working example, but so hopefully we should have something working within the next few weeks, and no doubt you'll see it on the discourse when it's not working. But we do have other development goals in mind. So we want to kind of incorporate various other additional hydrogen physics and features to entice more of the community to come join us, have better interfaces with external solvers, because there's a whole bunch of cool open source codes that we'd like to kind of work with and create a kind of mini consortium within Fusion, such as OpenMC, which is a really cool open source neutronics code. And we'd like to, a lot of us developers have access to HPC facilities, so we'd like to be able to design the code to actually be able to work on HPC systems, as well as things like performance benchmarking, so that we can make sure any new features that we implement don't kill performance. And we recently became an affiliated member of NumFocus, so we have a bit of money for some of this development now, which is very exciting. Any freelancers who want a bit of cash, we will come calling. So yeah, FESTIM is a powerful and accessible hydrogen transport code. FESTIM 2.0 is on the way, and yeah, thank you very much for listening.